Which of the following is an intermediate in the nitration of chlorobenzene? Well, in all of these rings, you can see that you have both chlorine and a nitro group added. When we do nitration, the nitrogen dioxide cation is added to a carbon that already has a hydrogen on it. And it adds, and then remember, the hydrogen leaves to reestablish aromaticity. So what we have to do is find an intermediate in which there's a nitro group on a carbon with a hydrogen. Here, the nitro is with a chlorine. That won't work. Here, there's nothing there but the nitro group. Here, there's nothing there but the nitro group. The only intermediates that have a hydrogen with the nitro group are these two. Now, if I look at chlorine, chlorine is a deactivating substituent, but it's an orthopara director. Here, the substituent is para. Here, the substituent is meta. The meta direction is not going to occur with chlorine, so the correct answer is this intermediate. Which of the following conditions will convert benzene into para-nitrobenzoic acid? Well, let's go through each one of these conditions to see what it would make. Right off the bat, I know that potassium permanganate is going to do nothing to benzene. So this is not going to be working. If I want to get a para-nitro, I cannot have nitro on first and then do methylation second, because that would make it meta. So anything that starts with nitro we would have to eliminate. The two left is that you put a methyl on first and then you do some other things. Here you nitrate, here you oxidize it to the carboxylic acid. So this would oxidize the methyl group to the carboxylic acid. If we nitrate first, it would be put in the para position. If we oxidize to the carboxylic acid, the nitro would go into the meta position. So the correct answer is the first one. What is the electrophile in the following aromatic substitution? So what electrophile adds to the ring? If I look at this, you would want to say that the chlorine is going to come off and put a positive charge here. So we would have a 3 carbon chain with a positive charge there. So you might have wanted to select this. But the problem is that is not a very stable carbocation. It won't stay there very long. Before addition occurs, you'd have rearrangement. A hydride shift would occur to cause it to become that. And we see that in the product. So the actual electrophile that's adding to the ring is this one. This is the catalyst, so it's not the electrophile. This is actually the nucleophile. The benzene ring is what's donating the electrons, so it's not an electrophile. And although this may be an intermediate, that's not the electrophile, it's the intermediate. So the correct answer to this question is this carbocation. What is the best method to make m-propylaniline? The PR there stands for propyl. Well, I know it's going to be 3 steps, and if I look at these selections, let's go ahead and see which one of these 3-step selections will actually give you the product that you want. Let's start at the top. If I put a nitro group on, and then try to put a propyl group on. If you were doing Friedel-Crafts, it wouldn't work. So this is not Friedel-Crafts. This is a Grignard reagent. But Grignard reagents react with carbonyls. They're nucleophiles, not electrophiles. So nothing would happen on this step with the Grignard reagent. Here you put a nitro group on first, and then you would use aluminum chloride and propyl bromide. This would be your alkyl bromide and aluminum chloride. So this is a Friedel-Crafts alkylation. But Friedel-Crafts alkylations don't work with electron withdrawing groups. They deactivate the ring too much for a Friedel-Crafts reaction to go ahead. So let's go ahead and try the Friedel-Crafts then, followed by nitration. If I do that, it would give me para substitution, so it can't be that. What if I do nitration and then reduce it to an amine? Well, if I do that, again, the Grignard reagent isn't going to do anything but deprotonate the amino group. This is a protic compound, and protic compounds do an acid-base reaction with Grignard reagents. Grignard reagents don't work with anything but carbonyls or epoxides. They're nucleophilic. We need an electrophilic reaction. Well, this one says aluminum chloride, and this is propanyl chloride. This is a Friedel-Crafts acylation. This would put a carbonyl adjacent to the ring and make it a meta-director. Nitration then would put it in the meta position, and reduction of hydrogen and palladium, not only would it reduce the carbonyl that would be adjacent to the ring, but it also would reduce the nitro group down to an aniline group. So the correct answer here is this one. What reagents do you need for the third step in this transformation? Well, you might be saying, oh, gee, I don't have ESP, but you can think through what are the possibilities. You know that if you use this last, that would put a carbonyl here, so it can't be that. And I can't do this as the last step because the sulfonic acid is a deactivator that won't allow Friedel-Crafts to occur. It wouldn't allow this to occur either. If I did this last, that would put the ethyl group would be on there, and then trying to put the sulfonic acid group on would cause it to go to the ortho para position. So you can't put it on meta when you have this group on the ring already. If I look down at right here, thionyl chloride and aluminum chloride, well, that's nonsensical. We don't have any kind of reaction that does that. What's the only thing that it could be? It could be reduction. If you had a carbonyl here and you add this group to it, that would go meta, and then when you use this reducing agent, it would take the carbonyl off this position. Which of the following carbons of the benzyl radical has the smallest unpaired electron density? Well, this is basically, can you draw the resonance structure for this free radical? And it uses the same ideas on how to draw resonance structures for looking at meta and ortho pair direction. So if I go and I move this free radical, if I move the double bond in here, the free radical would be here. If I move this double bond up here, it would put the free radical here. If I move the double bond here, it would put the free radical there. So you would have this free radical be in the ortho, para, ortho positions through resonance. 3 would have no free radical character, or very little free radical character. What is a major product of this reaction? Well, if I look at this reaction, I see on here, I have an ortho para director with the methyl group. So that will direct to this position since pair is already covered up. And then here I have a meta-director. So what are we going to see? We're going to see bromine being put into the ortho to the methyl group position. So that's meta. That's not anywhere, we don't expect to see that at all. We don't expect to see displacement of either group. This is the correct selection. Which of the following positions are activated for chlorination on the compound shown below? So if I look at this, I will see that there is a methyl group, which is an ortho para-director, and I see a nitro group, which is a meta-director. So this is an ortho para-director, so this is activated, and then this deactivates everything except for the meta positions, and these both are meta. So where are we going to see chlorination occur? Both 2 and 4. What intermediate is formed in benzene electrophilic addition? Well, when we go to do a benzene electrophilic addition, and we see the electrophile add, one of the double bonds is taken away, and the positive charge is on, when the electrophile adds to one carbon, there's a positive charge on the adjacent atom. So you lose a double bond. So it can't be an aromatic carbocation. It is not conjugated, and it's not aromatic. Remember, what is it that happens in the last step of a benzene electrophilic addition is that you lose a proton to reestablish aromaticity. So it's not aromatic. It's definitely not a free radical. It's a positive charge. And it's not a sigma complex of any sort. It's a pi complex. So the correct answer is the cyclohexadienyl carbocation. So which of these reactions, which of these substrates will undergo the Friedel-Crafts reaction at the slowest rate? Well, let's go ahead and look at what we have on the rings. Here we have a slight deactivator with an activator. Here we have 2 activators. Here there's 1 activator, and here there's 1 activator. The 2 activators would make it go fastest, so this would be the fastest of all of them. And if I compare these two, they're both activators, and the oxygen is much more activating than just a carbon. So the rate would be this is fastest, then this, and then this. This would be slower. Why? Because you have a chlorine on there as a mild deactivator, and it would slow down the Friedel-Crafts reaction. This is an intermediate in which of the reactions below? Okay, if we look at let's examine this intermediate. We can see that this is an electrophile has been added to a benzene ring, and let's look at the ring to see where the electrophile was added, because there's both a hydrogen and a bromine on this carbon here. The bromine or a bromine cation must have been the electrophile that added, and that this group was already on there. So let's look for conditions that would give that to us. Benzene isopropyl and hydrobromic acid would not have given that at all. That wouldn't have done any of that. Bromobenzene and doing a Friedel-Crafts reaction with isopropyl bromide, that would not work because we're not seeing that the propyl Isopropyl has been added, but it's a bromine that has been added. Isopropyl benzene with bromine and iron 3 bromide, that looks like the ticket to get this intermediate. Isopropyl benzene, light and heat, that won't give you anything. There's no bromine even there. So you know that's not correct. So let's go ahead and look and see. What's the correct answer? That one is. So here's a little bit of a challenge for you. Go ahead and try to figure out a synthetic sequence that will take you from acetophenone to meta-ethyl aniline. The triple arrows does not mean that there are 3 steps involved or 5 question marks, not 5 steps. That's just saying there's more than 1 step needed. So go ahead and try to figure out how you might be able to do this. Okay, the first thing I see is that the 2 carbons here are probably the 2 carbons there. And I could reduce this down to a methylene group pretty easily with either hydrogen over palladium or with the zinc amalgam and hydrochloric acid. But the thing is if I were to reduce it right away, that would make this group into an orthopara director, and I need to have this put on meta. So I need know that whatever I need to do is I don't need to reduce this right away. So how can I get a nitrogen on the ring? Well, we know that we can put nitro groups on and then reduce nitro groups down to amines. So the first thing that we're going to do is put a nitro group on. That's going to go on meta. So now that we have the nitro group on, we can reduce it. And if I want to use tin and hydrochloric acid, that would reduce just this down to this, but it would not reduce the carbonyl away. And if I used just the zinc amalgam and hydrochloric acid, it would reduce this down to the methylene group, but it would not reduce the nitro group. So to reduce both of them, what would I use? I would use hydrogen over palladium, and that would